Hey Eric,
Hello.
what do we have today?
It is some kind of spectrophotometer.
And it's a MacLeod Instruments Eskalab Spectrometer Alpha. Oh my goodness. And I think it's an absorption spectrometer that you put your samples in the left.
Well, I think you store them here, and I think this is where you actually take
measurements.
yeah. Take it out and you put it in here.
You're totally right. And then it has a dial here that tells you the wavelengths, and maybe it moves on its own. Wavelength release, I don't know. And then you get the absorption spectra, and then you know what kind of chemical composition you have in your thing. Hello and welcome back. This instrument is a donation from Alan Martin. Thanks, Alan. Although I usually concentrate on HP instruments, this one piqued my interest because it's optical. This kind of spectrophotometer is mostly used in life sciences to accurately measure the concentration of chemicals or cells in a sample. It works by measuring absorption in a liquid sample. The principle of operation is rather straightforward. You simply shine a light of specific wavelength or color in a liquid sample and measure how the light is absorbed by the chemical or cell you are trying to find the concentration of. By choosing the wavelengths carefully, you can maximize the absorption and therefore the sensitivity of the measurement while minimizing the contribution of other unwanted species. The log of the absorption is then directly proportional to the concentration of the species. It's called Beer's law and has sadly nothing to do with the beverage of the same name. Assuming you can measure the absorption of a few known samples to get the slope of the absorption curve, you can then find the concentration of an unknown sample by finding the point it corresponds to on the straight line. One of the first desktop instruments was introduced in the 1940s by Beckman. This one is from the 1960s, likely one of the early transistorized instruments, although the detector uses a photomultiplier tube. From what I can gather, Eskalab was a 1966 trademark for a system of clinical chemistry supplies such as pipettes, reagents, and cuvettes compatible with this spectrophotometer. Wait, where have I seen this business model before? From one of my favorite company? No, modern HP would never do that with the ink for its printers. I could not find any online information on this unit whatsoever. So we'll go in blind, starting with an exploration teardown. Maybe we can figure it out, and why not try to make it work. And I was told it works with a photomultiplier because I have a photomultiplier spare somewhere that I have put, I don't know where. I think that's the TNT in question.
Ugh, vintage dust.
Yeah, oh look at that. Look at that thing.
It's even got some frosted glass in the business end here.
The photomultiplier, another interesting animal, a super sensitive photodetector. It was still unbeatable as a single photon counter until not that long ago. It is a vacuum tube that works as follows. A photosensitive surface, the photocathode, is coated with a material that emits an electron when it is struck by a photon. It takes only one photon to create one electron. Then the electron is accelerated by a series of electrodes called dynodes that are at progressively more and more positive voltages. When the electron strikes the first dynode, it has acquired enough energy that it knocks out more than one electron loose from the dynode. These are further accelerated to the next dynode and create more electrons. This multiplying electron avalanche continues and is in effect an electron multiplier. It eventually reaches the most positive electrode, the anode, where the current is collected and measured. The multiplication factors are enormous, reaching millions, enabling a relatively easy single photon detection. In our tube, the dynodes are arranged in circles, so the trajectory of the electrons looks more like this. Powering our tube is rather simple, provided you have about 1000 volts available. Just connect the anode and the diodes to a dividing ladder of equal resistors. This is a cold tube, so there is no filament heater and associated current needed. This is great. The scale changes, I think it's... Oh yeah, it works. See how the scale changes?
I love that.
That's just totally awesome. Okay, yeah, you have 3 settings. 1, 2, 3. That's the party trick.
That's great.
Okay. It came with other boxes of optics. Oh, that's a grating. It's not a grating. It's a filter. You can see how it goes from blue to red. So that is a transmission filter. It needs a little bit of cleaning. Okay, after a microscope inspection, this is not a front face coating, but I can actually rub. Okay. Ooh, colors. Oh, cool. So those are interference filters. They're multi-layers coatings, and that gives them their very particular hue. It looks like it's almost like something that you would move and slide around.
Yeah, it's got that odd holder. Is that plastic?
Right, I'm not sure if it's for our instrument. So we have choppers. Half of them are all floating, not protected.
Oh,
All right.
Well, well, well.
Well, we have wells.
And it's got looks like a strip heater around it. Oh yeah, look, see, these are banana plugs on the back.
Oh, so you can keep your culture at the right temperature.
Oh, and then this would be a thermometer on the front here, 36, 37, and 38, presumably Celsius.
We need to find one of these holders. It might have to be quartz for it to work, which means expensive.
Boy, look at this.
Wow, I like the size of the meter.
That is a giant meter.
And then here we have the business end. Here's a chopper. It's smarter than I thought. It chops between the reference sample and the measured sample. So it does measurement versus reference.
Mm-hmm.
Whoa, this is the best kind, a dual beam spectrophotometer. This is so that you can measure the absorption of your sample and compare it to a reference sample with zero concentration, subtracting the effect of the solvent, medium, and the cuvette. In our case, as we'll see, a single detector is used, but a rotating Mayer chopper will switch the beam from going through the reference sample to going through the measurement sample.
Oh, this actually moves a shutter over here with some gratings in it.
Okay. Huh.
And then here's your here's the other part of the chopper, but it looks like it's got these, what are these, like light pipes or something?
It's an absorption thingy. It's right here, and it's just a filter. The rainbowy thing that we just cleaned is that. So.
Well, and they have the other thing on this side too. So it's got your gradient thingy over here, but on this side it's got several discrete little elements.
Oh, it does too?
On this side. Mm-hmm.
Oh, there's a tube that's supposed to be in there, and it's not in there. So missing something. So we have arc lamp, we have the board that's not connected to anything, and that must be the PMT, right? So that's a PMT, and that's...
Could be a PMT power supply or an
power supply, amplifier. Very annoying, we don't know what it is. So you said you had two discrete things?
Yeah, you can see it on the end now. Let's take a look in there. See, it's got that little holder with the different elements in it.
Oh, this one.
So it's got different markings here. It's got this continuous strip here, but then if you keep going, then here's one that says 340 and then aux.
Yeah,
so
which
that would be the two extra
was the
ones.
two filters on the sides.
Mm-hmm.
So the way this works illumination comes from here, and let's see, this mirror is down. It comes here, goes to your sample once, goes to the prism, goes to your sample twice, goes here to another lenses, goes through the filter, and here is probably a mirror, and goes through the PMT.
Mm-hmm.
And then when that is over here, I have to turn it around. So illumination will come from the light over here, bounce here, in there, through sample, prism, bounce the prism, other direction, comes out at the bottom, and goes into the detector. So it's a double pass through your cell.
Yeah, these little gratings here, I think, just have holes etched in it to change the amount of light that can pass through to 50% or whatever the number is.
Yeah. Optical densities to attenuate the beam.
Mm-hmm. There's another open tube socket over here as well.
Oh, dang it. They took 2 tubes. Yeah, we're missing a tube right there. Here's a fiber light pipe. So that's the one that goes and illuminates the sensor at the back of the chopper. Okay, so I get the general gist of the instrument. We are missing 2 tubes. You have some more interesting news.
I was inspecting the, I guess, power board on the back here, and there's some burn marks on the PCB material and the remnants of what used to be a resistor that somebody clipped out, and so we don't have that resistor anymore.
Either, so that's a basket case of an instrument. Yeah. You found where the missing resistor has been put?
It's just on the back of the board, but this is not factory. This looks like somebody tried to repair it.
Yeah. So you have more good news?
It just keeps getting better. I pulled the cover off of this, and it's a transformer, and it says bad on it. So somebody else has been in here before us.
Right. And we know by following the wire that this is a transformer for the high voltage of the PMT, which we now know works under 1.2 kilovolts. And if we follow the wires, this guy I think is a preamplifier for the tube signal. And the tube, we took it out. Here it is. It's very clean though, it was in there. And you can see it has 2 high voltage connection. That's for the multiplier ladder. The resistor for the ladders are in there. Here's the signal coming out. So we're missing a preamplifier. I think we're missing a rectifier over there. And the whole thing is bad. Is it worth reverse engineering? I'm not too sure. We could plug it in and see if the arc lamp comes on, if it's even worth it. I think this is a basket case. We took the high voltage card out. The lamp is connected directly to the transformer, and so is the motor. So see if it turns on. And nothing happens. Not a thing. If the light had turned on, this would have turned on. I don't hear a motor. Alright. Okay. Nothing's going to happen with this one. Yeah. So I really thought this was going to be the end of the video. It's missing stuff, some is marked bad, the light and the motor didn't even turn on. But I kept trying to reverse engineer the wiring of one of the missing tubes, and it progressively dawned on me that one of them might not be a tube at all. Maybe there is faint hope. So I've managed to get a little bit of life out of the machine finally. The first thing I figured out that this is a synchronous motor, and that this should have been a thermal delay relay. There is no 6.3 volt heater to it, and there's not enough contact. So I think this is one of those old tube relays with a thermal delay in it. And if I turn it on, nothing happens, but I'll play the delay relay. And that gives it enough of a kick to put it to the synchronous speed. So we have motor action. You can look at it over there. Whee! So that's nice. I also have taken the light out. If you can focus on it, there it goes. And the light was actually broken. That's why it didn't work. So the ampule is broken. And this is most likely a halogen light in a quartz envelope. So it can do some UV. And it's 6 volts. However, I replaced it with a 6 volt just standard halogen, and I jury-rigged it at the back. So back there what I have done is I've jury-rigged a regular little halogen 6 volt bulb that I had around. It's only 20 watts. And I put it on an XYZ stage so I can align it in front of the optics. And that's enough to get me going. I think you can barely see the red light over here. You turn the light even more down. Here we go. Infrared, red, and orange, and the colors. Red, green, and blue. And if we had the right bulb, it would go way into the UV. Okay, let's see if I can demonstrate the display if I just do it with the ohm meter. Yeah, I think I got something. There we go. Look at this nice meter. And it's nicely damped. That's one of the most beautiful large meters I have seen. You probably noticed that this is a very unusual meter. Yes, it works reverse. With no current, it is resting at the right, indicating the maximum reading. With current, it moves towards the left, towards the 0 indication. Another thing I forgot to show is that these are actually optical fibers, fiber bundles, and there's some light over here. So it's a light pickup from the fiber goes from the under here, comes back here, and there's some light sensors for the chopper. So the optical part seems to be working, and then you give it a little kick with the relay thing, and off you go. And now, of course, none of the electronics works at this point. But we got some chopper action, we got some light, we got some meter action. So all of a sudden there was some hope, and we enlisted the help of Master Ken to figure out our bad card. So Master Ken, you have reverse engineered the power supply?
Yeah, I traced out a schematic for this power supply, and there's more going on here than I was expecting. So it has 2 linear supplies here, so you get a positive and a negative. Has a little separate regulator here for diode bridge, and xenodiode generates a small voltage. But probably the most interesting part is the oscillator transformer and then voltage quadrupler here that's generating the 1000 volts.
And the capacitors don't look too good.
They're made out of cardboard.
Oh, those are the best. Very yummy, and something has grown out of this one, so I changed those first. So we have a tail of 3 capacitors. This one, that's the one that has obviously leaked, has no capacitance left. This one has no obvious sign of distress, and has more capacitance than advertised, 174 microfarads, and ESR is 0.2 ohms, so it's good. And then we have another one that's in between. This one has 1 point something ohm of ESR, which is not a good sign, and it has lost 2/3 of its capacitance. All right, change them all. I think I've found a replacement for the lamps. Problem is that it's 6 volts, so that's hard to find, but the best I found was an old Philips projection lamp, which is 6 volts, 30 watts. And it is a quartz envelope, so they are known as QTH, quartz tungsten halogens. It's sort of a regular bulb, but with an optically nice envelope, so you can image the filament. And I used this little support, and I cut a little piece of tubing, and I made it look like the regular lamp. And I noticed that I had to use some heat resistant wires because it gets super hot in there. The camera is not going to like it, neither are my eyes. Woohoo! It's extremely bright, and it's also much whiter. So that should be way brighter. You see the spot. And so I get a lot of deep reds, and I can get to the blue. Let me turn some of the light off. And look at that. I can go all the way to 400 nanometers, and if I put the special filter at 340, I still have some light. So that's because of the quartz envelope. And then you can go through the whole thing. Look at those nice and brilliant colors. It's better in person than on the camera, and then it goes super far in the near infrared. That's 700 nanometers. All right, pretty good. Also, between Ken, Eric, and me, we spent 2 days reverse engineering the boards. This is the power supply here, and it's indeed 3 power supplies, but it's more complicated than we thought. There's a power supply that's controlled by something else. It's incomplete here. And there's the high voltage power supply that's also incomplete, controlled by something else. And we found the other bits on the amplifier board. Eric did that one. And this is the part of the high voltage supply that we were missing. It regulates the gain of the PMT with an input from the zero trim pot, also from one of the fiber optics chopper pickups. It adjusts the gain of the photomultiplier tubes. There's yet a third board on the meter, and that board appears to be a ladder of resistors and diodes, so it's probably to implement a logarithmic conversion between the linear signal and the logarithmic indication. And then we were puzzled forever by the tube that we were missing. Now that we know that the high voltage regulation is already accomplished somewhere else, I don't think it's needed. My guess is that it's not a tube that's missing. This is a port for test during manufacturing, to test the optics and the PMT before the rest of the machine is assembled. And what else? And we figured out the thermal relay. I ordered one. It's a 115C2T.
1 week later.
Look at what I got. A new old delay relay. That's the real thing in the real package. Oh, I see some tube goodness. So that's a relay, apparently. Pretty. Something like that. Maybe. Maybe not. Yes. Yes. You focus. There we go, it's on. Is it gonna work? It spun the motor, but did it? It's supposed to be a 2-second relay. It's supposed to be 115C2, 115 volts, C normally closed, 2 seconds. T, that's the 9-pin socket here, but I'm not seeing it move. Maybe it does. You don't hear anything. It's in vacuum. You don't hear anything, don't see anything. Normally close. Get back to close. Oh yeah, I see it closing. It does close. Huh. It's bending back. And now if I turn it on, the contact separates. Oh, beautiful. All right. Okay, so I put the boards back. Time to turn it on. I think we understand enough of it. And I'm going to first check the main power supply. If we got anything. Oh, I hear the inverter. And I get nothing. No, I get minus 30 volts. Okay, that seems okay. There. Minus 70 volts. Woohoo! So on the front side of the thing, we get something. Can we zero it? Oh, it's not turning. Hold on a second. There we go. Can I zero it? Ah. Oh, I hear the loop regulating. Which is the reference, which is the sample? I don't know. Okay. If I... Okay, that must be the reference. And this is the sample. Whoop. The absorption goes up. And the reference, I hear the frequency of the regulation changing. Alright, I think it works.
That's easy.
More or less. I cannot quite get it to 0, which I should be able to do. Why can't I zero it? So I think we are starting to understand what we see. That's the signal of the PMT that's been amplified. The small peak is my measurement signal. So if I kill the measurement signal, the peak in the middle disappears, my needle goes up. And I think this is what controls the gain somehow. So if I put it there, if I kill it, it will bring up the gain. And what I am measuring on the needle is the height of that little bump that goes through the sample cell. The bump small goes up. Bump is high. So the higher the bump, the further this direction. And what this wheel does, as we had thought, it just acts on the power supply over here and lowers the gain of the PMT, and I see that happening, right? If I put it all the way to the right, the gain is lower, and therefore the height of my bump is lower, and therefore that goes here. So what that tells me is that the reason I cannot get to 0 is that I don't have enough signal going through the sample cell compared to the reference cell. And that's not an electronic problem, that's an optical problem. And I think I figured out why. I looked at the mirror, and it looks like the mirror has lost some of its reflectivity. Actually, you can see it. You can see through the mirror, which you shouldn't be able to do. Fortunately, with the machine came a few more optics. And we have a few extra mirrors. So I think what I have to do is change the mirror, and then I'll be good. This you can see the mirror part is oxidized. Let's take that thing out and see if we can fix that with the new mirror. You know, while we're at it, we can see the trick they use to reduce the amount of light into the sample cell. It's an etch plate with more or less with little holes that are etched in it, and it lets more or less light come through the cell in a calibrated way. Very clever. Alright, so here is our mirror, which is significantly pitted. And here's the new one. I'm going to try to remount this without breaking anything. Okay, let me put these back in. 1, 2. I have to put the card back in and see if we can zero it. Okay. I do have plenty of light, much more than before. Yeah, there we go. Yeah, I can zero it now. That was a problem. I can't see it over there too. I have much more signal over here. Now I can zero it properly. You can also see how much square my signal is over here, because the edges of the mirror were just corroded away. So it had a very smooth transition. Now it's nice and sharp. So what does that do? It does... well, it increases the gain. I finally understand how the regulation works and how they make the measurement of the difference between the reference cell and the sample cell. Basically, the PMT out comes through here, and that's the amplifier. And it comes out here, and that's the signal I have here. And that's the sample cell, then that's the reference cell, the sample cell, reference cell, the sample cell, reference cells as the mirror rotates. And then what happens, the output is common and goes to the two photosensors, which are two choppers basically, and they are those two things here. And one is open during the reference cell reading, and the other one is open during the sample cell reading. And so this one is open when the reference cell is being read, and it's fed into here. So here I have the reference cell reading, but inverted. This is just a peak detector that measures the negative peak of this green signal, and then that regulates the gain in the PMT. Look at the green guy. I'm going to change the signal in the reference cell by going to the next range. It goes down at first and whoop, it's corrected right away. This regulating loop changes the high voltage, so the gain is such that the signal of the reference cell is always the same. And now my sample cell is too high because this is the high absorption. So if I want to get it back to normal, and yeah, I blocked it. There you go. Now I am in range, right? And this thing can measure it. When it's time to read the sample cell, then the other chopper opens and feeds it to the meter. Now that I understand, it all makes sense, but man, it took me a while. This is the one that will be open during the reference cell, and you can see it goes from here to here. So that's when the mirror is open straight to the reference cell. Then for a while they are both closed, and then now this one will open, and that's when it's measuring the sample cell. And then it will close before the mirror is out, and then now they are both closed and the cycle repeats. So that's how they do it.
For the electro-curious, I'll explain this again with the full schematics, which are quite interesting.
Feel free to skip this elevator music section and rejoin the live action at 4206. Here is the power supply. There are two regular power supplies for -30 volts, -70 volts, and two precision reference voltages developed by Zener diodes. There is also an unregulated power supply over in the corner for maintaining the sample heater block at 37 degrees C. That's the one that had the burned resistor. Now I understand why. Since it is on all the time, the power resistor probably got a bit tired of that. But the most interesting part is the high voltage supply. It starts with a lower voltage oscillator which develops 80 volts at a few kilohertz, which is then fed to a high voltage transformer, the black thingy with the bad sticker on it. But the transformer itself was not bad, fortunately. It is then followed by a diode capacitor voltage quadrupler. Its output is about 1 kilovolt. But something is missing. Point TP17 should be the ground return for the power to the oscillator. Instead, it goes to a wire which escapes into the machine. We found the other end of that wire on the amplifier board, which is this schematic. It arrives at TP2 and is eventually connected to ground as we expected, but not before going through the Darlington pair Q11, Q12. Oh, very clever. Now we can adjust the current return and therefore the 80 volt oscillator, and therefore the high voltage supply. Whatever controls this Darlington pair controls the high voltage, which then controls the gain of the photomultiplier tube. But what controls it? Let's turn our attention to the optical signal detected by the PMT. It enters at TP7, then gets amplified by Q1, Q2 and Q5. They form an op-amp of sorts. There is an additional trick bias circuit with a negative peak detector formed by CR1 and C2, then amplified by Q4 and Q3. This is used to automatically adjust the bias voltage of the input FET transistor just at the knee of its turn-on. More old-school analog trickery. Anyhow, the output of the PMT amplifier, which is the inverse of the yellow curve that we just were looking at on the scope, is the time multiplexed readings of the reference cell and the sample cell. This is then fed through two optical switches depending on the position of the rotating mirror, which act as the demultiplexer. One switch transmits only the readings of the reference cell towards the bottom of the schematic. This was our green signal on the scope. There it encounters another negative peak detector formed by CR4 and C3. The reference cell level then goes on to Q10, used as a comparator, which then controls the high voltage supply via the Darlington pair that we discovered earlier. This results in a servo loop control that automatically adjusts the gain of the PMT so that the reference cell reading is always amplified to a precise preset voltage. This voltage corresponds to the zero reading. The target voltage is finally adjustable by the 10-turn zero pot on the front of the instrument, and we finally got that to work. But wait, there are two other pots on the side of the instrument labeled 0.5-1 and 1.0-1.5, which are tied to our big scale knob on the front of the instrument. These further fine-trim the PMT gain when the scales are changed. This is to make sure that the scales are well butted on our trick scale changing meter. That is, if you read 0.5 max deflection on the lower scale, you should adjust the pot so it also reads 0.5 minimum deflection when switched to the 0.5-1 scale. So let's go back to the output of our PMT amplifier. The measurement from the sample cell is connected to the meter via the second optical switch at the appropriate time. It then goes on to this complicated circuit at the back of the meter. What a mess! But after a little cleanup, the circuit looks like this. Ha! Now I can make sense of it. There is a big capacitor for transforming the signal into DC by simple averaging. Then I recognize a diode ladder. This is an analog computer trick to transform a linear input into an arbitrary function. Returning viewers of the channel will have recognized the circuit from our HP 3300 episode, where a diode ladder was used to transform a triangular waveform into a sinusoidal waveform with very low distortion at that. That was quite impressive. Here it is used to generate the log curve. The reading on the meter should be the log base 10 of the absorption, so we can plot Beer's law directly. Which gives us the final explanation for the two last adjustments. One is to move the ladder up and down, the other is to adjust its spread. These two adjustments are on top of the instrument in front of the meter and are critical to the precision of the instrument. These were almost certainly factory adjusted and are not going to be trivial to get right. But now that we understand everything, it's time to return to the live action and do the final adjustments. So I think we got all the mysteries out of this figured out, and then we could calibrate it again. These two are for the calibration of the logarithmic scale, and these three are for the overlap of the scales. We've also changed the big capacitor here. I still need to order the correct one, but it makes the regulation come on much faster. So now my remaining problem is to have the ranges overlap. 0 something. And I should be at 5.1 over here. Oh, much better. I think now I can get it. Should be 5.1. There you go. So now I'm pretty well stitched together. This is at 0.5. Switch here. It's back at 0.5, and I put it to find a wavelength where there's an absorption of 1 density. There you go. Like that. There should be a hair below 1. Okay, so I'm all stitched. I need to do the 0 gain though. For that, you know what I can do? I could find a way to measure it off the oscilloscope. Okay, I think I've found a way to calibrate this. So if I don't put any sample, here my maximum measured on the right shoulder is 135, and then if I divide that by 10 to the power 05, I get 42.8. So that should be what a perfect 05 density is. And I'm almost there. So that should be density 0.5 very exactly. And here I am reading density that's slightly too high. So I need to change one of these spots. Okay, this one is loose. I'm being lazy and not having the right tool. Okay, I need to bring up my socket tools. This one. The pot is turning. I better do that with the thing off. I think part of our problem is that the pot is not in good shape. It's all corroded, and I cannot get it out. This is completely stuck. Oh, that was a toughie. I had to Dremel partially through the nut to finally get it off. Okay, so I think it was just surface rust. I was able to rebuild, clean it and rebuild it, and now it's all fine and dandy. It has some little jumps over here, and I can always order a new one. At least we can try to adjust now. I think I have it. This is the right now calibrated to exactly 0.5 density. If I take it off, back at 0, or very, very close. So now I have to just redo the continuity of the scales and we should be good. After another agonizing hour of scale readjustment, I think we can call it repaired. We're ready to make measurements. Okay, time to do some biology experiment. I'm completely out of my element, but I'm going to try to extract chlorophyll with acetone. So this is my little vial acetone. This is sage. Well, I might as well do something that smells good. It's somehow getting there. It's getting green. So it looks like my sage juice is getting really green. And also I have found, after much difficulty, some cuvettes that work, because those are not standard size cuvettes. Standard size cuvette is 12.5 by 12.5. Found one that works. It's a 5mm cuvette, but that has also a smooth phase in the other direction for fluorescence, so we're going to use it that way. That is my chlorophyll juice, and I'm going to make a dilution series, approximately 3. Then 6. Alright, pretty dilution series here. Okay, 3.8. Light green. Or darker green. Already in the next range. Set all the same way, 6.65. Even darker green. Oh, 1.0. And hopefully when we change scale, we find the same thing. We do. And now we have 1.3. And then 1.30. Okay, the only thing that we don't have is, I don't have a real 0 because I'm missing a cuvette. I should do the 0 with that on and another cuvette on. Alright, let's plot that. So that's our newest experiment. It's straighter than before. Mm-hmm. I know that the scales are well butted to each other, but I'm not 100% sure that my method of doing the first scale, 0 to 0.5, gives me the right log through the scale. The 0 point is good, the 0.5 point is good, but in between I'm not sure how to calibrate it exactly. Well, hindsight is 100%, as they say, and while I was reviewing this long video, I realized that there is a jumper on the meter board to do the adjustment correctly. You measure the linear value voltage with the jumper off and then put the jumper back on to make sure that you get the proper log reading. We'll do it right in another life and won't let that ruin our first beer. But all in all, from an instrument that we were about to abandon on the shelf of shame to a fully functional one, I think we did pretty well. See you in the next episode. Oh, hold on for one more minute. Master Ken just came up with this brilliant idea to do a Bier's curve with gin. So for the next experiment, Ken has gotten us something very special that is Canadianese.
This is a special type of gin that changes color with pH.
These two are undiluted, but as soon as I put water in it, it must have changed the pH.
Okay, give the patient 10 cc's of lemon juice.
It's pinkifying big time. This one over here is baking soda. That should re-bluify it.
We'll get some foam probably. Oh yeah, look at that color change.
Oh, so hopefully that will help us calibrate better. And we are going to scientifically demonstrate that they are pink and blue. So this is the undiluted gin. So it's absorbing on the whole band, and then it has a dip in the blue as you expect, right? Yeah, it's 460 nanometer blue. I take the pink one. Right here, I have the dip in at 630, so it moved all the way from one end to the other almost. Interesting. Okay, well, it's going to be really hard to calibrate our instrument with this, as it changes color when we dilute it.